This is a review for your Chapter 7 or Unit 7 exam, and the exam itself will actually be pretty straightforward and pretty consistent. And what I mean by that is there will be a lot of questions that, if you think about the Unit 6 exam, there were a lot of things that would have just been different questions. Like there were 20 completely different questions. They had no rhyme or reason. In this one, there will be something that's more like, for the following 4 or 5 questions, do this for this specific kind of thing. So as long as you kind of know how to do one of them, you probably will kind of know how to do the others if you're at least keen on the different shapes of things. So that's actually a good bonus and plus for you. And unfortunately, for some it might not be, because you might not know how to do any of them. But again, fortunately, maybe one hint will help you with the rest of them as well. And I'm heavily going to stress, when I review this, I'm just going over all the California state standards. I went over the Common Core state standards in the Unit 6 review, so I won't do that again, because these generally apply with every single thing that you do. So just make sure you watch that one, or you just pay attention to what you did last time, and I think you should be okay. But the ones that will be heavily covered on here are 1.0 as far as state standards. You'll have 1.0, a little bit of 5.0, I suppose. That's 4.0. Yeah, a lot of things with parallel lines, but kind of things that you already know. Just knowing that they're parallel is good enough. Yeah, there'll be stuff on this stuff as well, but really coordinate geometry will be another big one. So the big ones to cover really, to me, are 1.0. I think 5.0 only because we talked about it so much. CPCTC, I just think that's a huge thing. So something I'm going to be covering a lot in terms of explanation of things. I really want you to get the big picture of that. And coordinate geometry, because I want you to be able to know how to interpret your graphs and prove things not just by using properties of shapes, but using the coordinate geometry to explain the property of a shape. And we'll talk about that a lot with 1.0, because we'll talk about the definitions as well. Okay, so 1.0, properly apply terms, theorems, axioms, and deductive reasoning. So I talked about deductive reasoning last time, and I'll just kick off with that because I don't want to give really any examples. But for example, actually, when you're doing deductive reasoning, you are leading facts into a conclusion. You build up evidence, and you have a conclusion based on your evidence. Like, we know that triangles are congruent from side, side, side. In other words, if I have these 3 sides in this triangle, and these 3 sides in this triangle, there's no other way that these 2 triangles could be manipulated in any different way other than exactly how it is, with the corresponding angles and the corresponding parts. And so you deduce that if all 3 sides are congruent, then the triangles themselves must be congruent. That's an example of just deductive reasoning, building up a case and drawing a conclusion based on evidence. Axioms are things that we kind of have to assume to be true to build on other things. For instance, quadrilateral by definition is a 4-sided shape, but like a rectangle, for instance, it has 4 right angles, and maybe I might ask you to prove that the sides of a rectangle are congruent, okay? But if you could not do that, maybe one thing we have to say that we have to assume by axiom is that the opposite sides are parallel. And that can be proven true because 2 right angles are supplementary and add up to 180, and they're same side interior angles. If they're same side interior angles and they're cut by a line transversal, same side interior angle supplementary means the opposite sides are parallel. Just like that and just like that. Now that they're parallel, I can prove it by drawing a diagonal, getting myself alternate interior angles, and reflexive property here, and I have angle side with angle side. Triangles are congruent, therefore these opposite sides are congruent. Things like that. So an example of an axiom there is saying that the opposite sides of a rectangle are parallel. I don't want you to, well, I might have you prove that to be true, but those kinds of things. Theorems, things like the triangle midsegment theorem. Okay. This one says if I have a triangle and I use the midpoint of two different sides, such as that guy and that guy. Let's assume those are the midpoints of A, B, C. We call these points E and F. Okay. And I construct a line through that midpoint, and I'll use the blue color just to make sure you see the different triangles here. Okay. The segment that's drawn between two midpoints is called the midsegment. Now this is just one midsegment. In fact, that looks a little off. This is just one midsegment. Another midsegment would be with a midpoint drawn here and the segments between those 2 points as well. So like that. So if you can see this midsegment between these 2 points, etc. But I'll stick with one for now. I'm just letting you know a triangle has 3 midsegments just like it has 3 sides. So if you draw a midsegment, and a midsegment is technically drawn from the midpoints, then the midpoints divide AE and ED or EB into congruent parts. Oh, I skipped D. Oh well. And AF and FC into congruent parts, congruent sides. So that's one thing that the midpoints do. Now the midsegment itself, EF, is exactly half of BC. The reason for that is if you take AF, let's say this length is X. If this length is X and this length is X, so the entire length of AC is 2X. So if AC is 2X, the ratio, so check out this triangle here. If I look at this triangle AFE and I compare it to the lengths in the triangle ACB, okay, the side ratio of AF to AC is X over 2X. Cancel out the X's, you get 1 over 2. So you get a similarity ratio there, a side ratio there of 1 over 2. Same with this. If AE is length Y and EB is length Y, then the entire length of AB is 2Y. So the side ratio of AE to AB is Y over 2Y, which is also 1 over 2. Now that doesn't yet say anything about EF and BC and all that, but if I wanted to prove these triangles are similar, for example, AEF and ABC, I have 2 side ratios there which are proportional. If I could get the third, that would be awesome, but I have nothing based on that. But I do have 2 congruent angles. Now I can't say angle E is congruent to angle B right now. There's nothing that I can say about those 2 being congruent. The only reason I could is by saying corresponding angles, but I don't know yet that these lines are parallel. But I do know that angle A is congruent to itself. You can see angle A in this triangle and angle A in this triangle. And now I can say angle A is congruent to itself, and if that's the case, I have a side ratios equal with these side ratios, and I have an angle in between. So side angle side similarity conjecture says that AEF is similar, triangle AEF is similar to triangle ABC. So if they are similar, keep this in mind because I think you know something about similarity. If the triangles are similar, then I have all corresponding angles congruent in some way. So now I know that E and B are congruent, and F and C are congruent, or at least this F and that C. So now I have corresponding angles here and here, which means these lines are parallel. So I actually skipped a statement I was making earlier, and I'll go right back to it. So EF is parallel to BC, and you remember that these were all 1 to 2 side ratios, AE to AB, AF to AC. And because these triangles are similar triangles mean each side related to the other one in the other triangle have the same side ratio. If it's 1 to 2, then EF to BC is also 1 to 2. So if I take EF and multiply it by 2, I get the length of BC. So that's the triangle midsegment theorem in a nutshell. It's these 2 mathematical, or things you need to know, that if I draw a midsegment between 2 sides in a triangle, then first of all it constructs a smaller triangle. So the base, or the midsegment, is exactly half the third side of the bigger triangle, and it is parallel to the third side of that triangle. So this is just one example. If you recall, I drew the other two mid-segments before. Let's make one purple. Okay, let's say that's between B and C. So this, and here's where I'll write D, because I forgot it the first time. I hope I don't have the hiccups for too long. This segment ED has now constructed, first of all, a mid-segment, so that makes these two parts congruent. And as you know, these two parts are congruent, because this is still a midpoint. So ED is exactly half of AC, and it is parallel to AC. Okay? And it creates congruent angles, so this angle C is also congruent to this right here for the same reasons that we did before. And this angle E is congruent to that angle A. They're also corresponding angles. I know it gets marked up a little strangely, but you can go with that. So that's the triangle mid-segment theorem, and I could have connected FD as well. I could have said same thing here, half of this and parallel to this. Okay. See, no other theorems I want to say, but I do want to talk about, here, let's see if I don't want to talk about it in another part. Yeah, I'm alright. I might talk about it a little bit in 4.0, but just in general, two-column proofs. Let me explain it for the people who still don't quite get it. It's the same as a flowchart proof, only it emphasizes a certain order that you want to put things in, and you must provide backup reasons for something. So a two-column proof works such like this, or just like this. I have statements, my facts I want to speak of, and nothing can be an opinion. Everything's the evidence that you build up. And the final statement is normally your conclusion, the thing you try and prove. So I have two triangles I want to prove congruent. I have these given things like angle A is congruent to angle D, and that's given. Okay, so that's a reason. It was given. They provided it for us. Now there might be something like AC is congruent to BD for the, here let's say AC for the reflexive property. Okay, so the important thing with this really is that here's where you might provide theorems. Like I might have these two triangles here, and then I'll say this is congruent to this from the or this is exactly half of this from the triangle mid-segment theorem or something like that, or it's parallel to it. And the reason's triangle mid-segment theorem. And you conclude the triangles are similar by side angle side similarity, stuff like that. So you say triangle something is congruent or similar to triangle something by side angle side similarity. So that's how two-column proof works. You basically give yourself a list, statements and reasons. I might talk about that in 4.0. Okay, but there are a lot of terms, and I just want to write all of the ones that I can think of. Mid-segment, I already talked about. Excuse me. Is the segment joined by two midpoints in anything, really? I guess in anything, but the triangle is where you have the mid-segment theorem. Bisect, kind of the same thing. A mid-segment technically bisects two sides, but think of bisectors. There are two types. There are, I guess they call them segment bisectors, where if, like, let's say I had a parallelogram, terribly drawn one, by the way. This diagonal, which is another, I'll just keep writing things as I think of them in parallelogram. Okay, the diagonal is the segment joined by opposite angles. Opposite, got to think about that one. Okay, the diagonals in a parallelogram bisect each other. And what that means is it divides them into equal parts. So a bisector is something, bi means two, sect means parts, two parts. And these two parts happen to be equal, but it bisects the segment. So segment bisector, and there's also something called an angle bisector, which would divide an angle into two parts. And I'll stress the lettering of this right here. If I have this ABC right here, let's make it a triangle, and I draw AD. AD bisects BAC. If I said that AD bisects angle BAC, what that means is I have divided angle BAC into two congruent parts. So that means that angle BAD, notice what I did there, angle BAD, not just angle A, is congruent to angle DAC or CAD. Okay, so if AD bisects it and it's an angle bisector, that means these parts are congruent. Notice how I labeled them. I had 3-letter assignments because now it's divided into two. Okay, so that's what a bisector is, and that's how it can work. So it works similar to a midpoint for segment bisectors, or a midsegment, kind of, in that it divides it into two congruent parts. Okay, let me talk about more shapes as I think about them. So parallelogram, all these are four-sided shapes I'll talk about. Parallelograms, four-sided, opposite sides are parallel. Diagonals bisect each other. Okay. Opposite sides are congruent also. Consecutive angles are supplementary. So these two guys would add up to 180, this plus that, or this plus that. If these add up to 180 and these add up to 180, then these must be equal to each other, because only that same angle measure can add up to that one to be 180. So opposite angles are congruent. And what else did I say about parallel? That might be it. But yeah, there's a parallelogram right there. You can say adjacent angles in the diagonal are supplementary, but I don't think that's as important. Okay, specifically, so a parallelogram is a generic type of a rhombus, or a rhombus is a specific type of parallelogram. In a rhombus, everything's the same, only all sides are congruent. So it's like a square that you skew over because the angles don't have to be right angles. But like a square, the diagonals are perpendicular bisectors of each other. So when I said the diagonals bisect each other in a parallelogram, in a rhombus they're perpendicular bisectors. These make right triangles all the way around. So they're all 90 degrees. And that was a rhombus. Okay. We get some other ones out of the way, like rectangle and square. Just make sure to write them. I'm not going to define all these. I just wanted you to get a good example of what those things meant. You know, a square is a rectangle with all sides congruent. There's a trapezoid with one set of parallel opposite sides. And I just want you to keep in mind another thing when I talk about base and height. Okay. In a trapezoid, you technically have two bases, one called B2 and one called B1, and you know the area based on those letter assignments. Well, if I draw an altitude, which I'll mix with height, if I draw an altitude, which is that imaginary line that's kind of drawn perpendicular to your base, that is your height. Your height is always perpendicular to whatever base you give out of something. So you use the formula with this h. The h isn't right here. That's just a diagonally drawn line. Now, it's not the diagonal. The diagonal actually goes between opposite angles over there, like that. So just want to make sure you know height or altitude, which is, again, an imaginary line drawn. I guess it's not imaginary anymore, but it's not a side. And it's drawn perpendicularly from a vertex to a opposite side. Okay, so there's your trapezoid. Kite, which we don't really talk about too much, only because it is pretty confusing and we haven't had too many problems with it either. A kite is really focused on the diagonals. We talk about these opposite sides being congruent a lot, but the diagonals are more important, mostly because that's what's used in the formula, but also because it's the first time we really don't look at diagonals diagonally. See, when I say diagonals, I'm not talking about the sides, even though they're drawn like, you know, they're slanted. These diagonals that go straight up and down, you remember what diagonal is, the sides, the segments opposite, or drawn from opposite angles. These are perpendicular to each other, and one diagonal bisects the other only. So it's not done both ways. This one does not, this diagonal does not bisect this diagonal, only one way. And that's what creates these other things. And I do believe then that these are congruent and these are congruent. So the diagonals bisect are angle bisectors, and I think these are congruent as well. Everything like that. Alright, so there's your kite. What else did we do? We had, slope. Just talk about slope in general. Okay, that's rise over run. Speaking of which, parallel, because we mentioned that, perpendicular. Okay, with slope, if two lines are parallel, that means they have the same slope in different y-intercepts. I won't really talk about y-intercept on the exam. If two lines are perpendicular, or segments, then their slopes are opposite reciprocals of one another. By the way, I'm not going to spend this much time on the other things. This is really just talking about all the terms and stuff. I think some of the other ones I probably won't even really cover, because I did last unit. Sorry, we did this one, this one, this one, this one, and this one. So I honestly won't even talk about some of them. I probably won't even discuss Pythagorean theorem, only to say this is how it can be used in different places. Okay, opposite reciprocal means if I have a slope like 2/3, opposite means changing the sign. If it was positive, make it negative, negative, make it positive, and then flipping the numerator and denominator, so -3/2. So the slope 2/3 is an opposite reciprocal of -3/2, and when they cross, like I say, up 2/3, up 2/3, down 3/2, they make perpendicular angles. So when you're proving something, so by the way, when I'm talking about proofs and stuff, I am kind of covering this, so I think it's okay. Or 3.0, if something says, JC believes that these lines make, or that this square drawn in this graph is perpendicular, or that this shape, is she correct? Why or why not? And then you say, well, no, because the slope of this one is 4/3 and the slope of this is -5, and those are not opposite reciprocals. Therefore, these do not meet perpendicularly. So that kind of covers that and coordinate geometry, because we talk about slope. Okay. Now distance is straightforward, just the distance between two parts, and when they're diagonal, you can only count in a specific way. You can't actually just count; you have to use math. Let's see, what other terms have we used? Let me see if this book has anything. No? Okay, I think I'm pretty good with the terms. So those are the different kinds of terms that you'll use, and kind of look at those and you'll get a good gist of them. You'll use words like congruent, but you've seen that before. Okay, check. Like I said, the other ones won't be nearly as long, some I'll kind of just skip. Judge the validity of a logical argument disproved by counterexample. Now this is just a huge concept in this class in general, though. Everything I talk about is regarding logic, prove, disprove, etc. So I'm not saying always disprove. I want you to also prove, but you can't prove by example. Just remember that. Proving by example means giving a number example to support reasoning. And the reason why you can't do that is because I might still find something where I can disprove it. I still might find another set of numbers. So make sure your proofs, whenever we talk about proofs, like when we proved area of a trapezoid, we didn't give numbers, we gave the general gist of what this is. We know that there are two bases, let's arbitrarily name them B1 and B2, and we have a height, h, and if I draw a diagonal, I make two triangles, and this area is B1, half B1 times h, this is half B2 times h, add them together, whatever. That's where the area comes from, and we prove that not by giving number examples, by saying, if this base is this, oh, this works. Because we didn't really know anything about area that way. But like I said, disprove by counterexample. Well, you know what? The other one was really proof by contradiction when I talked about the perpendicular thing. So I might throw in a proof by contradiction, even though the standard isn't really covered in this unit. But proof by contradiction is saying, let's first assume that that these 3 points join and make a right angle. Okay, make the assumption that they do. And this point is 0, 6, and this point is 1, 2, and this point is 8, 3, whatever it is. Well, now you take the slope of this thing. By the way, I'll make sure I define slope for you. It's also m, y2 minus y1 over x2 minus x1. So the change in your y values, how much do I rise or fall, in this case from A to B, and how much do I go over? So if I fall 4 units and I go over 1, then my slope for AB is negative 4 over 1, which is negative 4. My slope here is I go up 1 and I go over 6. So my slope of BC is 1 over 6. Now this was kind of close, and that was by accident. If this was 1 over 4, then these would be opposite reciprocals of one another. And if that was true, then this would be perpendicular. And that would be judging the validity of the logical argument. But I now proved by contradiction, I said, first let's assume that these are right angles. If that's the case, then I would have opposite reciprocals. Now let's go ahead and calculate the slopes and see if they are. And because they're not opposite reciprocals, boom, that is a proof by contradiction. Disproof by counterexample is saying something like all quadrilaterals with 2 right angles are rectangles. So there might be something here and it says, I have a rectangle, I have a right angle here and here, therefore these 2 must be right angles. And you can disprove that. You can say, well, all I need is for all these things to add up to 360. This plus this is 180. So this plus this just needs to equal 180. This could be 70. This could be 110. Therefore, so my disproof by counterexample is saying I could make these 2 guys right angles. I know those don't look like it. Now this one's obtuse and this one's acute. And they're different. So that's a disproof by counterexample. The other one was proof by contradiction, and like I said, I probably should have kept that standard in there. Just I wanted to keep 8 and not get it too big. But at least now you know for next time. Okay, prove basic theorems involving congruence and similarity. This is where you're just going to use more 2-column proofs. So I just want to make sure that you know how they work and really what you have to do when you use proofs, because we're still a little shaky sometimes. When we use evidence and such. So here I'll say, for example, I had a homework assignment. I have to bring it up though, 1 second. Let me find the actual problem first. It was assignment number 11. And we had a 2-column proof here. Just assume the left side is statements and the right side is reasons. Okay. We had this tic-tac-toe looking thing right here, and I had A, B is down here, C, and D, and we had this whole line called AD, and this whole line called EH, something like that. Anyway, so we wanted to prove that A was congruent to D. Now these are not corresponding angles. If they were, then we would just say that immediately. So we had to say A was congruent to B because they were alternate interior angles. B was congruent, sorry, this should be congruent to C because these are corresponding angles. They're on the same side of a transversal. And they are, now it said AD was parallel to EH, by the way. AD was parallel to EH. That's what makes these work. So these are corresponding angles. And then we said A is congruent to C then by substitution. And I actually helped you out on that step. Now, B is congruent to D, or I'm sorry, well, yeah, I can say B and D, or I could say C and D. I can do this either way. C is congruent to D because vertical angles. I think they gave you C is congruent to D, that's why I'm sticking with that. Now A is congruent to D, not because of corresponding angles, because I said if A equals C and C equals D, then A must equal D. And that's substitution again, or the transitivity property theorem, whatever it's called. Transitivity means replacing one thing to the other. If I like eggs, and eggs are protein, then I like protein, something like that. They don't always work one-to-one, because that one's a little different, but that's an example of transitivity, going from one to the other, transitioning into them. So, like I said, that stuff's kind of wonky only because I think some people sometimes make things up. Make sure that your reason makes sense to you. Okay? You can't make things up. Otherwise, you can't make a statement. I always talk about court cases, and it always has to do with murder. But you can't prove something. You can't make a statement without a proof of something. You're trying to convince yourself as much as you're trying to convince everybody else. Okay, in similarity, just make sure that you know with reflexive property two things. One, reflexive property does not mean reflecting across or whatever. It just means the side is shared. So this segment is congruent to itself by reflexive property. It doesn't necessarily mean this reflects over. It could, but that has nothing to do with reflexive property. Reflexive is spelled with an X. Reflex. Not I can't even spell. Not reflexive. So two different things there. And then also reflexive property in angles, like I did earlier with the triangle midsegment theorem, says that an angle is congruent to itself in this triangle and in this triangle. Like I said, shared angles and shared sides. That's different from vertical angles. You can ask more questions on congruence and similarity, but I think we've touched on that a lot in class. Something else we've touched on a lot in class is CP/CTC. And I can't stress enough what this means. And I might as well go over like an example and find one. Let's see. Let me find one. This one is from review number 2. It's number 4. I'll just go ahead and use one for you in case you didn't know how to do it, so we can talk about it. I'll do the example and then explain what we did, and then I can move on for you. So I'm just drawing what they have. Okay. I have a C, a D, an E, and an F. By the way, when we talk about quadrilaterals here, well, let's say I'm explaining this quadrilateral, and for all intents and purposes, this may be a parallelogram because that's the tool I use, because that's what it looked like. When I name this quadrilateral or like a triangle, quadrilaterals are a little more important because alphabetically you should say C, D, E, F. The problem with that in assigning the letters is that when you say C, D, E, F, you mean that you're going from one point to the next along the sides. So here's C, here's D. If you were going to do E, F, this point would be E and this point would be F. Okay, and again, the reason is when you're drawing the quadrilateral, you want to know that they all run in a sequence. C to D to E to F along the sides. Now this one does not run that way, so it's not always listed alphabetically based on that. This quadrilateral could be called C, D, F, E, but it could not be called C, D, E, F. So you'll know when you do quadrilaterals a couple of things if you have this naming assignment. Number one, C and D have to be a segment. So do C and E and D and F and F and E. And because of that, number two, C and F are not only not segments, but they are diagonals of each other. And D and E are not only not segments, but they're also diagonals of each other. So make sure that that makes sense. And this isn't the only way I could have named this. I could have named it E, F, D, C, whatever, as long as I'm drawing along this way in consecutive order. So I can't say E, F, C, D. Okay. So think about that when you are taking the exam. Okay, here are some givens. Angle C is congruent to angle F. EF is parallel to CD. So it is your job to prove, as they ask you, that CE is congruent to EF. Excuse me. Now notice anytime we do a proof is never excuse me, a proof is never one statement and reason. In other words, I have to build up facts to make the proof. Otherwise, it's not a proof. It's something that we've already learned before. Like, it's something that's already found in evidence. In a parallelogram, we would know that CE is congruent to DF. The problem is, in this case, we don't know this is a parallelogram. So this is kind of deductive reasoning if you think about it. In order to prove that these are congruent, I can maybe do something such as prove that this is a certain kind of shape. Like, I can see that this maybe should be a parallelogram, or perhaps an isosceles trapezoid. Now, in this case, that's not true. I'm just saying, or a rhombus, or a kite, or whatever. Figure out what kind of shape it could or should be. And if you can prove that it's that kind of shape, then you can prove these segments are congruent, but only after that fact. Or in this case, if I prove these two triangles are congruent, then I can prove its corresponding parts are congruent. And I can already see two corresponding parts, angle C and angle F. And because these opposite sides are parallel, these opposite sides are also probably congruent. Now, I don't know these opposite sides are parallel. If I did, then I know it's a parallelogram. If I knew it was a parallelogram, then I know these are congruent. So like I said, there are a bunch of different ways that you can do this, but if they're saying prove segments, parts of these triangles or quadrilaterals are congruent, then that means I have to do some work to prove that the whole thing is congruent. And that's what CPC-TC is all about. It's corresponding parts of congruent triangles are congruent, or congruent polygons in general. I can do CP-CPC. If I have two pentagons that are congruent, they also have corresponding parts which are congruent. We just use CP-CTC because everything is built off the basis of triangles, pentagons included. We're going to do this a little more in Chapter 8, but I can draw a bunch of triangles here. If I can prove one triangle congruent to the other, yada, yada, yada. All right. So going off that fact, though, oh, by the way, this is CP-CTC because I don't have two separate quadrilaterals that I'm proving congruent anyway. So let's go ahead and work this one. And then and then I kind of just want to talk about 10 and 15 and 10 and 17 and skip 7 and 15 for the most part. Okay, let's start this off. So I'm even kind of going to skip the statements and reasons. I kind of just want to talk about them, and you can write them as you go. Just pay attention. First of all, I would list givens. Angle C is congruent to angle F. Segment CD is parallel to segment EF. Okay, so those are givens. Now, based on those givens, that can help you do some things. C and F, not so much. It can help you build a case of congruent triangles, but it doesn't really lead to other things, at least not yet. Okay, but CD and EF being parallel is important. Now, this does have to do with 7, by the way. Use theorems involving parallel lines cut by a transversal. These are parallel lines, and here's a transversal. Okay? With that, I have alternate interior angles, and that pops up a lot. A lot in parallelograms. I mean, you know, in parallelograms, but in quadrilaterals when you have the diagonal and the parallel lines. So this angle is congruent to this angle. This is angle CDE, and this is angle FED. So angle CDE is congruent to angle FED because alternate interior angles are congruent. Now I only know that because these lines are parallel, and this diagonal is a straight line. And that's known as my transversal. Okay. Finally, I can say DE is congruent to itself. That's the reflexive property there. And it's a shared side among these two triangles, between these two triangles. Okay, so now I have built a case for angle, angle, side, with angle, angle, side. And then I can then say that my two triangles are congruent. So I have triangle CDE is congruent to triangle FED. Did I do that right? C, D, E, F, E, D. I did do that right. The only thing I didn't do right was this statement. I was going to say something was wrong. This should be DF, by the way. CE is congruent to DF. If you're doing this on your sheet right now, then you would know that. Anyway, the reason behind this statement, and I should have written more statements anyway, this should be like the fifth statement, is angle, angle, side, congruency conjecture. Angle, angle, side with angle, angle, side. Now, here's where CP/CTC kicks in. I'm going to first look at the CT, congruent triangles. I have congruent triangles. Okay, let's go and erase that. Here's the rest of it. CP, corresponding parts. Which parts correspond? Well, let's go and number these off. 1, 2, 3, 1, 2, 3. Angle 1s are congruent with each other. Angle 2s, D in this triangle, E in this triangle, are congruent with each other. We could have used third angle theorem or whatever it's called to find the other ones anyway. Angle E in this triangle is congruent to angle D in the other triangle. Okay, the third angles are congruent. Now the segments in between are congruent as well. Here's the important part for this proof. CD is congruent to FE, 1, 2, and 1, 2. CD and FE are congruent. DE and ED, 2 and 3, are congruent. That's the reflexive property there. And the last one, CE, 1 and 3, and FD, 1 and 3, are also congruent. So corresponding parts are congruent when I have congruent triangles. So I'll rewrite CP/CTC. Okay. So what that means is that, well, I mean, so now here's my proof. I now have CE is congruent to DF by CP/CTC. Now this reason is so crucial. I only got this because of what I drew evidence from before. And I know I gave this example in class, so I'm just going to go and use it again, again, talking about court case stuff, because when you're trying to prove something, draw conclusions on it, we say that. Okay, last review, I said, if you killed somebody, you're trying to figure out somebody killed somebody, and with that, you want to see if the person had the intent to kill, right? You're trying to charge him a murder, and you're saying he had the intent to kill, therefore, whatever. Now, you can't prove he had the intent to kill. Let's say that that's an issue. There's a road blockage. I can't really prove that, or I can't really make that statement in general. However, you find all this other evidence and blah, 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 and once you figure out he's guilty, then you can conclude if he's guilty, that's also inferring that he intended to kill. So the one that I used in class was same kind of thing. If you're accusing somebody, again, to kill somebody else, and you're trying to pinpoint the fact that they were at the scene of the crime at that time on that night, blah, 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 blah. So he was in the warehouse at the pier at 8 p.m., whatever. And now you can't make that claim by anything. You don't have any video evidence, you don't have any witness testimonies, nothing else like that, at least nothing proven to be true. But you find all this other stuff. You find the gun. You find the fingerprints on the gun. You find the DNA on the body. You find the blood on the clothes. This guy's been acting crazy. This guy has been talking about killing this person in his journal, blah, 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 blah. Okay? You get the evidence, you convince the jury. They find him guilty. Because you find him guilty of murder, that means he must have been at the scene of the crime. So even though you couldn't have proved that he was at the scene of the crime without, you didn't have video evidence, whatever, if you prove that he's guilty, then he must have been there. So CP/CTC follows the same way. And I know it's kind of a weird concept because I jumped straight from murder to triangles. I get that. But CP/CTC follows the same exact logic. I don't know these parts are congruent. Well, now I do. Just ignore the tick marks. Let's go all the way back here. Okay. I don't know CE and DF are congruent. Oh, this should be a D now. Nothing for me to state that. I don't even know that this is a parallelogram. I don't even know these triangles are congruent. I don't know anything about this. I just know this, and that. Okay? So you can't just make a statement based on it. And furthermore, you have to make sure that you remember what the end proof thing is. Some people kind of stop with their proofs. They end up proving triangles are congruent, and that's it. You have to make sure you know what the proof is. Okay? But what I can figure out is I can circumnavigate everything else. I can figure out what else is congruent. I can build a case, draw evidence, ask questions, whatever. And then I can prove the triangles are congruent. And when I prove the triangles are congruent, if the triangles are congruent, they have identical parts. These are the two identical parts in these two triangles. Okay, now I can't stress that enough. This cannot be overstated. I'm merely saying it so much, and it might sound like yes, 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 he's saying it over and over. But for some people, it's not being grasped. And it needs to be understood. This is a basic concept. It's not overwhelming. Yeah, you can have very long and tedious proofs. That rectangle one was a big one. And if you still have trouble with CTC in proofs, even if you get the concept, you might want to look at that one. In fact, I don't think I did it online. I might have to do that one online sometime, not here. If you have a question on it, just let me know online, and then I'll do it again. But this can't be overstated. And CPCTC is just a massive concept that is just so overlooked in general. It's not just about proofs, but it's just about reasoning in general. All right? And it's not just using math. You can tell I keep talking about this murder trial thing. Now, there are other things that you can use about that too, and you use it in real life, you just don't know it. So that's why I state it so much. Now, the other important thing is that whenever I ask a question on an exam, I show the standards which I cover. When you see 5.0 as a covered standard, you might want to consider the fact that it has to do something with CPCTC, and you might want to explain that. Okay, so keeping that in mind. Okay, I'm going to kind of skip 7. We've talked about it quite extensively, but just know when you have parallel opposite sides and you can draw a diagonal, then that's considered to be a transversal. And if that's the case, then you have alternate interior angles. Or same thing with parallelograms, by the way, like this. Ugliest looking parallelogram right there. These segments act as transversals to these parallel sides. That's why these are supplementary, really. Because these are same side interior angles. You can see that, right? These are same side interior angles. That's why they're supplementary. We call them consecutive angles. I gave another example by overflowing the parallelogram into another one and lining them up as adjacent angles. That's why I was calling them that before, because we didn't talk about consecutive yet. But yeah, that's why they're supplementary. So that's 7.0. Check it blue. Okay, 10.0, compute areas / perimeters of polygons, triangles, and quadrilaterals. Let's do the formulas. Okay, first of all, perimeter means adding up the sides. Not really another way for me to talk about that one. If I add up the sides of a perimeter, then I get the perimeter of it. Now the perimeter is in single dimension units, and I'll talk about that later. Areas, I'll defer. Now I won't explain why in any of these. You're going to have to come up with that, or we talked about it in 7.1.2, I think. Area is the overall coverage, and it's in square units. The area of a rectangle, and I'll just put R, is base times height. Same with a rhombus, by the way. Area of a rhombus is also base times height, so the fact that it's R is pretty good. Area of a triangle is half base times height, half of a rectangle. Area of a kite is half D1 times D2, where D1 and D2 are the lengths of your diagonals. Area of a parallelogram, oh, by the way, area of a parallelogram is also base times height. So, by the way, a height in parallelogram and rhombus is this guy, if this is your base. Okay? Just making sure you know that. Here's height, here's base. And the area of a trapezoid uses two different bases. You add them together, take the average of them, and multiply them by the height. Or, similarly, B1 plus B2 times H over 2. Same thing. Do I have any others? Square is base times height also, but they have the same side lengths. Okay, now the important part here, units and square units. Why do we call them units and square units? Well, if you think about a square itself, when we squared the length of something, whatever, then that's why you can think of it. So this is 3 times 3. Let's say 30 times 30, because I'll talk about like a room. A room can be 900 square feet, for instance, where this is 30 feet and this is 30 feet. Now the perimeter, you can tell, is obviously different. You add up the sides, and basically, here's how I'd think of it. And you can think of it this way as well. Let's say that each tile in the room, like there are all these tiles, let's say they're all 1 foot. You know, all the tiles in the room, boom, 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 boom. They're all 1 foot across. And you want to walk across all the tiles. If I want to take the perimeter of this guy, I'd start on this tile and take a step on this one. That's 1. Take another one, that's 2, 3, 4, etc. You walk across 30 tiles this way, then 30 tiles that way, 30 tiles, 30 tiles. And assuming that you count some tiles twice, like you have to count the corner tiles twice each time, you would end up with 120 tiles counted. You walked 120 feet. So the perimeter is 120 feet. The area is saying, let's go ahead and walk these 30 tiles across. Now let's go the next row of tiles and walk across those. Now let's go the next row of tiles and walk across those. And let's keep going until we do it 30 times. So we walk across 30 tiles 30 different times. That's why we cover 900 feet of walking distance. So area is all about coverage. Perimeter is just in terms of a distance. A rim around a fence, whatever else. So coverage is taking something like, here, let's go and take this rectangle, for instance, or that's a square. Let's go and take this rectangle. I go across this way, some amount of feet. Now I take that every single time and I expand it. I cover that much, this amount of times. So the big difference between area and perimeter, obviously you know the difference, but between units and square units, that's where there's that difference. And that if I just said 900 feet, yeah, that's fine, only that would be taking 900 feet and going out this way. And we don't want to look at it like that. We just want to call them square feet and saying, okay, we're talking about coverage overall. Now, it's not always in squares just because it's 30 by 30. It could have been 20 by 30, which could be more accurate to this classroom anyway. Or it could be a lake. The surface of a lake could look like that, and there's some area here. Now, this is very impossible to compute. I shouldn't say impossible. You have to use calculus to compute something like this. But you can get general. You can find circles in here, get the areas of those, get a rectangle here, and a pentagon here or something, add up those areas, and you can get a rough estimate. But we'll do circles later. Okay, compute. So that was compute areas and perimeters of polygons. Let me make sure I don't want to say anything else about that. I kind of do, but it'll be with coordinate geometry. Okay, and I'm going to skip Pythagorean theorem with one exception, and it has to do with coordinate geometry. So the rest will be based on coordinate geometry. I have a pair of axes here, and I want to find the... Let's find out what this is, and I won't even know. Let's say this is A, B, C, D. Now remember, when I say A, B, C, D, I have to run across like that. I can't say A, B, then C, D. Let's use actual lines to connect these, and I promise I'm almost done. Sorta. Okay, now remember, this isn't drawn to scale. And I don't know what numbers I'm going to pick and if they'll work or not work in a good way. So A, let's say, is 210. B is 5.1. C is 11.5. And D is, let's see, that's 11. Let's call this 9.11. Hey, 9.11. Okay, and I want to figure out what kind of shape this is. If if there's a unique shape behind it, like this could be a trapezoid or whatever else, and use reasons behind that. So using coordinate geometry, including slope, midpoint, and distance, etc., I can do things with this. Not so much with midpoint, but using slope and distance, I can figure out what kind of shape this is. So think about this. And by the way, distance ties in with Pythagorean theorem. That's why I'm going to talk about it. If this was a rectangle, okay, then the following would be true. Opposite sides would be congruent and parallel. Diagonals would bisect each other. All angles would be congruent. Well, I'm sorry, and they'd all be 90 degrees. Which in quadrilateral, if they were all congruent, they must be 90 degrees. Okay, so this is an example of having to be able to do something to look at whatever. If I wanted to say that the opposite side, because I want to talk about Pythagorean theorem first and get it out of the way. If I wanted to find the distance, if I wanted to say the opposite sides were congruent, that would mean I could calculate the distance of 2 points, like AB, compare it to the distance of DC. If the distances are congruent, I'm well on my way. I'd also have to do the same with BC and AD. Now you can maybe assume that these already won't be true, but these aren't drawn to scale, so let's go ahead and not make that assumption right off the bat. Now if they are congruent, that doesn't necessarily mean I have a rectangle. I still need all angles to be 90 degrees. But let's go ahead and get that started anyway. I mean, this might not be a rectangle at all. This might be a parallelogram. Doesn't matter. Now, to find the distance between A and B, here's where I want to use Pythagorean theorem. I can either use distance formula and remember this big mumbo-jumbo thing. Doesn't matter which way you write it. I can remember that, or I can go ahead and just say I know Pythagorean theorem. I just need to find the distance of this vertical line and the distance of this horizontal line. Now the distance between 10 and 1 is 9. The distance between 2 and 5 is 3. So this is a right triangle with legs 9 and 3. And this hypotenuse, I can just call it a little c for now, is the square root of 9 squared plus 3 squared. So 9 squared is 81, 3 squared is 9, so 81 plus 9 is 90, so this is the square root of 90. So if this is the square root of 90, then I have a good start. So let's go and do the same thing. So remember, that's just Pythagorean theorem. I'm doing a squared plus b squared equals c squared, and I'm solving for that c, this little c right here. Distance between 11 and 5 is 6, and the distance between 9 and 11 is 2. So this is 6 squared plus 2 squared, which is the square root of 40 right there. So obviously these aren't the same. They're not even close. So I can already I can already rebuke this being a rectangle. It can't be a parallelogram. It can't be a rhombus. It can't be a square. Oh, by the way, if something is not a rectangle, then it's not a square. Think about things that way as well, because a square is a specific type of rectangle. It can't be a parallelogram, if I did or didn't already say that. It could still be a trapezoid. You have to figure out, excuse me, you have to figure out if these are parallel, though. This could still be a kite. Okay, so that's kind of how you figure things out. You start calculating based on that. So that's what I want to see on the exam as far as knowing whether something is something or not by using the features of coordinate geometry to talk about them. And I used Pythagorean theorem to talk about it by covering the distances of things. But coordinate geometry, I could still also talk about slope and midpoint and distance. Okay? If I want to find the midpoint of a diagonal, and I compare it to the midpoint of another diagonal, then maybe I say that those points are intersecting, that they both meet at the same point, and that the diagonals bisect each other. The midpoint formula is taking the average, midpoint is taking the average of two coordinate points. So if I took the average of 5, 1, and 11, 5, 5 plus 11, sorry, there's going to be another bell, a small bell in 5 minutes here. 5 plus 11 is 6, 16, 16 over 2 is 8. So I go 8 over, and I'll go 1 plus 5 is 6, 6 over 2 is 3, so I'll go 3 up. And this point here is 8, 3. That's just an example of some midpoint. So I might have you use triangle midsegment theorem on the exam if you find two midpoints and find the distance and blah, 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 blah. So think about that. Slope. If I want to say two lines are parallel, I'm telling you right now, if you say on the test it's because they look parallel or because they're flat, you are just, I'm just going to discredit that. If we're talking about coordinate geometry and 17.0 is one of the standards, that's only if 17.0 is one of the standards, you better say something about the slopes. If I want to know this is a right angle, or the diagonals are perpendicular bisectors, whatever, and they make right angles, okay, you better say it's because this slope is the opposite reciprocal of this slope. If you want to say these two lines are parallel, it better be because these two slopes are the same. And you better calculate that and find your reason, or you know what I mean. Or to say, if I wanted to see that this was a trapezoid, I'd compare this, and I don't know where my B and C went. I'd compare AB with DC. I'd compare the slopes of them. If they're the same slope and they're two different lines, then they must be parallel. Okay, that's a reason, and that's proof, and that's using coordinate geometry right there. And you know, I don't want to go overboard with it. That's kind of what I want to talk about with coordinate geometry. Using the shapes that we know. It doesn't matter if it's a triangle. It doesn't matter if it's a kite with weird fraction numbers. It doesn't matter if we're finding the equation of something with weird decimals and all that stuff. But that is coordinate geometry. Using geometry in coordinate space, you know, on a coordinate plane. And it's very perceivable and it's very possible. Just make sure you know the properties of the shapes. And you know what it means for a slope to be whatever, whatever. We talked about it with those things up there. Okay, I don't know. I'm kind of done. I don't really want to say much more else about this. I'm sure you don't want to listen at all anymore either. Common Core State Standards, like I said, I covered in Unit 6, and here are the California State Standards and how they apply to the unit. So make sense of those things. Ask questions, because I might have flown right over a concept, and you might want to talk about it more. So whatever you have for me, go in and throw it at me. But I hope that this helped and it made sense. All right, so go ahead and ask in the forum.